Hi, everyone. Welcome to the speaker series. Today, we're joined by Chang She, who is the CEO and co-founder of LanceDB, which is a developer-friendly open source database for multimodal AI, very close to what we do at Samsara. And Chang is a serial entrepreneur, and for much of the last 20 years, he's been working on tools for data science and machine learning. He's actually one of the original contributors to the Pandas library. And then just immediately before founding LanceDB, he was the VP of engineering at TubiTV, where he focused on personalized recommendations and ML experimentation. We were also fortunate to meet, I think it was maybe a couple of years ago, talking about Samsara when you all were at an earlier stage. And we've been fortunate to keep a connection and a partnership. And so that now we're using LanceDB internally. And we're very excited to have you here today to talk to us about what's next for LanceDB.
Absolutely. Thank you, Evan, and really excited to be here. Thanks everyone for taking time out of the day to join this talk. All right. So let me get started here and share my screen. I'm also joined by my colleague, Ayush Chaurasia. He's going to take over a little bit later in the talk, and if we have time, run some demos which hopefully will be interesting for y'all. All right. Cool. So let's get started. I'm gonna skip over my self-introduction since Evan already gave that, but just super excited to be here today to be talking about AI and retrieval. I think today what we're going to talk about is sort of from where we sit, we see a lot of kind of broader AI trends in 2025. Wanted to kind of bring those up and see if you guys kind of see the same set of problems, both within Samsara and also maybe within the customers that you guys are supporting. A lot of these broader AI trends, I think, are posing new kind of infrastructure challenges, data infrastructure challenges for a lot of the companies that we talk to and work with. And so I've distilled some of them and maybe a few kind of solutions and how we're designing Lance and LanceDB to meet those challenges. And then, thank you to all of you who've kind of pre-submitted questions. We also, there's a few points that I've kind of interspersed through the talk of what I call the practitioner's cheat sheet of should you do this, should you do that, what works well, what doesn't work well. And we're going to talk about some of these at a high level, and happy to dive into more discussion if we have time later on as well. And then, I'll try to keep this super interactive. Like, feel free to interrupt me at any time with questions. And of course, we'll save hopefully plenty of time at the end for Q&A as well. So without further ado, let's get started. So I think number one trend that we've been observing this year is, 2025 is the year of AI agents. And what we see is that there is production success across many enterprises and many verticals in legal, in healthcare, finance, code gen, and of course, across many multimodal verticals as well, like robotics, to that successfully deploy agents into production for a variety of tasks. And what's really interesting about this, about the future, is that this can kind of give way to a new wave of like AI first or AI native. I think YC called it like full stack AI companies, meaning let's say like legal, for example, if you are a really great legal AI company, your first move might be, okay, I can serve all of the law firms that are incumbent in the field. But what's to stop a new entrepreneur or a new seasoned attorney from saying, hey, I'm going to start a new kind of law firm that's fundamentally based on AI agents for legal tech, and just really revolutionize the whole legal field. And you could see this playing out in a lot of different verticals. um, especially the ones that might be tightly regulated and haven't experienced a ton of process and technical innovation. So this is also like a really long-term, interesting long-term trend to watch. And of course, if you don't believe, you don't have to take my word for it, right? Like if Jensen said it, it must be true. But if you don't believe Jensen, you can also believe kind of some data, right? So this is what I look at. I don't know how many of you've seen the recent news around Neon, the object store kind of version of Postgres. Neon was acquired by Databricks for I think $1 billion or something like that. And one of the really interesting stats that was highlighted in the news release was that 80% of new Neon databases are provisioned were created automatically by AI agents rather than by humans, which this is sort of real hard evidence that agentic workloads are just growing explosively. Okay, that's trend number one. Trend number two that we're seeing is all AI is becoming multimodal AI. And what I mean is we're kind of moving way past just plain text vector search that on the input end, a lot of retrieval is now extracting data from multimodal sources. So PDFs, slide decks, and images and videos, and making all of that searchable. And on the output end too, you have, of course, multimodal generation. So you might be generating text with some images or with videos. And the multimodal generation itself is becoming much more guidable and controllable. And we feel that multimodal is an interesting term because we think about multimodal right now as just different data types, right? Images, audio, video, with their kind of text plus one of those modalities. But in addition to data types, if you're building AI models or AI applications, your workload is also multimodal. So it's not just about search or it's not just about like OLAP, but you need to be able to retrieve from your data. You need to be able to compute aggregates and run analytics for evaluation, for building dashboards and computing metrics. You need to be able to do large scale pre-processing for that data, right? So, between the raw data and the cleaned up data that you're going to serve or train, there's often fairly complicated or sophisticated data pipeline of transformations that it goes through. And then number four is, of course, the training workload, whether even if you're still building a retrieval application, you may end up needing to do some sort of fine tuning or even training your own like re-ranker or embedding model. Right. So data types are multiple modalities. Workloads now are more diverse. And then, of course, you need to have some of those work is done offline in a more lakehouse context. Some of that work becomes done, in a serving online context. So the context in which is also multimodal. Okay, so number three is this is something maybe a little bit like less lower level, but MCP, the popularity of MCP has really exploded this year. I think starting with, it was released last year, but it's sort of like not that many people paid attention to it. And at the AI Engineer Summit in New York this year, all of a sudden it kind of blew up. And there's been a ton of attention, I think a lot of exciting development. We feel that overall, it's not yet production ready. It's missing a lot of things, but the direction is very interesting, especially the fact that it's a first sort of solid attempt at creating this composability layer for different AI tools and data sources and allowing the model to access them with this uniform API. Yeah, so, and I think if you search like LanceDB MCP, for example, this is just one tool, and there's already a bunch of community effort to integrate LanceDB into MCP as one of the options for your model to use in your applications. It is less. It's missing a lot of fine-grained controls. It's sometimes hard to direct behavior, and there's a lot missing in terms of like service discoverability and just emitting more context to the model from over this API layer. But I think it's worth paying attention to and keeping a watch on. All right, and the last thing I want to say, kind of at a high level, is that we think about the LLM as like the destination for our workloads, right? Like we do retrieval, then we augment the prompt, then we feed it into the model. I don't know, like we have run a for loop on the agent, right? And then we feed some state plus the context into the model, and the model spits out something. But I think as we see in 2025, especially even started last year, LLMs are now becoming an integral part of your data processing pipeline, right? The simple example is generating and embedding, right? It's not an LLM, but embedding model. The LLM is also being used to extract data. So if you have, let's say, like images and use LLMs to extract a text description, for example, that's an example of what we call LLM as UDF as part of your data processing pipeline. And the challenges that brings is, the LLMs tend to be quite large, right? A lot of folks are using using OpenAI or a third-party model API to not have to deal with the inference. But then you trade off cost as you scale up, and inevitably then folks want to have the solution to run inference in either within the same worker pod as they're running the pipeline, or sort of as a separate service via some sort of ray serve or k-serve type of service, right? And then of course, when you do this kind of large scale processing, the fact that it's less deterministic than other kinds of transformations creates challenges around how do you validate your transformations, how do you have repeatable pipelines and predictable results. But those are super interesting because LLM as a UDF is very effective in sort of doing complex transformations in an easy to use and easy to create kind of command and prompt. Okay, so I think there's tons of like interesting things happening as well. Those are the four that we observed that we felt like were super interesting and relevant, especially for folks like yourselves managing lots of data and connecting it to the model and building applications on top of it, right? And so in terms of the evolution of what we see in AI is, 2023 was a lot of experimentation. 2024 was when enterprises, larger enterprises especially, experimented with putting the first few AI features into production. And the big trend this year at the enterprise level is a lot of enterprises are going all in on AI and expanding from one AI feature to, hey, we want 10 or we want 20, or we ship 5 but then have 10 follow-on features that extend those things, right? So I think folks we see across different market segments and verticals are really going all in on RAG applications, agentic applications, and of course multimodal. And what that so what that brings us to is this need to scale AI in terms of the scale of traffic, the scale of data that you need to manage, and the breadth of applications that you need to manage. And so we are still in a world where I think folks first think about, okay, let's pick a vector database as the platform on which we can build all of these AI use cases, and um, um, and use that to kind of serve everything and try to be kind of the source of truth for a lot of this. And maybe you have to augment that with another system, but generally this is sort of the um, platform that folks are thinking about. And it's kind of natural because it is the first and only like AI native database, or it's the first kind of new category of databases that came up during the AI native era, right? So it's pretty natural. But the problem is that vector databases aren't enough. And going back to traditional kind of lakehouse architecture, that's also not enough, right? Because what happens is you've got this pressure from both ends, right? You need to ship more, and then a lot of individual teams are kind of creating their own AI stacks, right, to be able to move fast. So they take on this full stack challenge themselves. And so the infrastructure challenge is actually like getting, infrastructure teams are being squeezed from both ends to say, how do we create this unified platform that, one, we want to be able to scale without bankrupting the company. We want to be able to serve a variety of use cases, and we want to actually, we don't want to hinder, but we actually want to improve our time to market for a lot of these. And so I think vector databases is good for something like if you want to scale up, or some vector databases are good for scaling up the vector search side, but they're generally not very good at serving a wide variety of use cases, right? They're really only good at that search workload, and most of them are really only good at storing vectors. And so in order to create this unified platform, like bringing a vector database in is just not enough. You need, and then you'd have to like have some sort of metadata store, and maybe you're storing a bunch of other stuff on S3 and having to manage that locally. And then you have to stitch together all these systems, right? So what ends up happening in a lot of customers that we see early on is like the infrastructure teams are spending all of their energy sort of holding these different pieces together and are not able to spend enough resources and time to kind of move up stack and really get to the heart of the problems and serving all of the application teams that need all these AI capabilities. And then of course, like traditional lake houses can't really do the job either because they were designed for tabular data. So it's hard to manage embeddings, it's hard to manage the multimodal data, and it's hard to do a lot of the AI native data transformations and workloads that you need in this architecture. Okay, so there's a question. What are the other use cases other than search and RAG for an embedding store? Yeah, so I guess maybe for embeddings, so let's say like we see a lot of our users and customers using embeddings for agentic workflows. So retrieving the right kind of state, retrieving the right kind of context for different stages of that agent, right? And then plugging it into the agent. So it's short or long-term memory. And then you can use that on the training side offline. So if you're fine-tuning or training a model, the embeddings can help you curate your data set, right? You want to make sure that you have a good distribution in your training set and that covers the edge cases that you're maybe like aware of and then you want to cover. And then you can use the embeddings to do things like data deduplication, right? So especially with generative use cases where for Samsara, imagine like if you're capturing frames from videos, you might end up having lots of frames that look kind of similar. And if you're using some of those frames to try to address issues or do data exploration, you wanna say, hey, like I'm only going to show or include one out of this set of like, nearly continuous frames that look pretty much the same. There's a lot more use cases out there as well for embeddings. Right. And then and it's not just about the sort of model generated, like LLM generated embeddings, right? So if you remember from recommender systems, right? The recommender systems and personalization, that uses embeddings as well. You can have like collaborative filtering embeddings, you can have metadata embeddings, and a lot of our customers actually use all three of those to create this new generation of like AI native recommender engines and personalization systems. Cool. So to illustrate some of these problems, right, we can just quickly walk through what we call LM-powered data pipeline. So this is from, this is basically how one of our engineers, before he joined us, he was running his own startup using LanceDB to create um, agent application that basically acted as like an automated um, Q&A bot for his kid's school, right? So, uh, you know, you have basically this is an application that had this Q&A interface into LLM plus a RAG prompt, which of course you need the vector embeddings for to do the search, and that's created by this embedding model from the chunks, which is created from this text, which is then created by doing two things. One is doing text extraction from images, documents, audio, video, and then sort of having LLM prompts to maybe like generate text from some of these, and then chunking them up and embedding them, right? So pretty simple to start, right? This is easy to build, easy to experiment with. But then once you go into production, you start finding all sorts of problems around like you weren't retrieving the right answers. You maybe like the model would then start hallucinating, all sorts of things not uh, production quality, right? So first thing you would add is some sort of eval, right? So then you can have you can record the history, and he did this by putting this in a different LanceDB table. And then you can actually have the LLM as judge to evaluate some of these things. And then you can run, of course, your own custom eval process offline. So there's an online process that's like LLM as judge, and you can immediately know during the interactive session to regenerate the answer. And then, of course, offline, you can have this custom eval process to generate additional evals. So using that, he was able to say, hey, like, instead of doing the vanilla RAG, we're going to do hide. So we'll talk about that a little bit later. And then add re-ranking to that. And that improved the retrieval quite a bit. But then to get to that next level, he then had to deal with feature engineering, right? So maybe adding metadata to the chunks and then embedding both of them, and then um, being able to do sort of a bunch of other tricks as well. But let's talk about some of these first before we kind of lose the context here. So number one is hide. So I'm not sure if I can see the screen, but like maybe if I can ask a show of hands, something where like have you guys all already tried hide or are currently using hide within Samsara applications, or at least have heard of it? Okay, cool.
Just to note, we have used it a few times internally, but I don't think most teams are using Hide.
Got it. Okay, cool. Yeah, I'm curious to hear about your experiences. But certainly this is something that we recommend to everyone as something to try first to improve their RAG scores. Just by you can play with it a lot, like single answer, multiple answers, guided prompts. And this is because it's so simple to do and you can test it right away, that it tends to be sort of low hanging fruit here to try. The main trade-off here is it adds latency, right? So if you really want really fast answers, this may not be possible, but typically what we see is the generated answers tends to be much closer to the data that's in your vector store or embedding store than the question itself, because you have less control over the what kind of question and what words in the question the user gives you.
One question. What's your thought on, or your experience, instead of embedding the answers, let's say potential answers, you could also create potential questions and pre-embed them. So kind of getting the documents closer to questions instead of getting the question closer to documents. Have you tried that, or what's your experience with this?
Yeah, I think, right. So like any technique where you can create some synthetic data even that has a good chance of bringing the questions and answers close to each other in the latent space, will have a good chance of giving you better results. I think creating like embedding the questions or creating a bunch of questions, the main thing that I've seen is like it works really, really well in POCs. The I think where it needs a lot of tweaking is you really don't have any control over the verbiage that the users will use in production. And so it could be the same exact question, but the wording could be totally different. And so you'd have to maybe it's like it's the same answer, but you generate like 10 different ways to ask the question that then gets associated with the answer.
Yeah, makes sense. Thanks.
And so yeah, so I think this is where it's still a lot like this is where it's more art than science. Then there's a lot of trial and error. So there's no like simple formula of do this and it's guaranteed to work, but it's very much like, well, it depends on your data set and depends on your users. Number two is I think especially for multimodal data, late interaction, multi-vector kinds of approaches are really pretty good. And so this is something that I think, well, so the Copoly and CoQN came out last year. I think there's a new released paper. I think Ayush has the link that essentially what we do is we don't even go through this like text extraction or OCR recognition phase. It just chops up image embeddings or chops up the image into patches, embed each of the patches like it would in token embeddings in Colbert, and then you do this late interaction retrieval step. Now, the good thing is we see pretty good accuracy without any parsing, so it really simplifies your pipeline, or can. And the trade-off is that it's heavier weight, so it generates a lot more embeddings. The retrieval is generally a little bit slower. So there's a bunch of tricks you can do to speed that up with minimal loss um, in accuracy. And so I'll send out the slide later so you can look at some of the research reports that we've put out. Okay. Let me take a pause here, just read some of the questions. Okay, hide. Right. Okay. Yep. Yeah, I would love to do this later too, like, if did you guys run into any problems with hide and like whether you're using it now or why you didn't decide to use it. Okay. And then so we see a lot of folks doing data extraction, right? So your typical baseline you would use, right, is like off-the-shelf tools, your PyPDF, PaddleOCR, EasyOCR kind of Python tools. Those are So free and easily pip installable. For tables, like you can use Tabula. It's a little bit more complicated setup, but at least it's free. And then you have like AWS Textract and Llama Parse. And Textract and Llama Parse are interesting too because there's a lot more sort of meta instructions you can give it to kind of steer the extraction. So we see folks have good results from either of those. And I think the main trade-off there is, of course, it's not cheap, especially for folks who the folks who tend to need that level of accuracy also tend to have a lot of documents, and so that can get expensive, especially as you scale up. And of course, there's a kind of the LLM approach where you can use a VLM to then kind of recognize some of the data, extract that out manually without using these like canned tools. And then fourth is, if the documents tend to fit a pattern, we can always go back to pre-AI days and do like localization plus recognition. And for if you know what the template looks like, that actually can be a reliable approach that we find people fall back to, at least if like on first attempt these like off-the-shelf tools don't work as well as you would hope. And then I think also out of the list of your questions, you also mentioned like GraphRag as a possibility. Yeah, so with GraphRag, what we see is basic vector search that then provides entry points into a graph traversal. So the advantage is it gives you this option to explore really complex graph relationships, right? Like in some sense, the embedding space is also a graph, but it's sort of implicitly built, whereas the graph database, it's an explicitly built graph where you're controlling the kind of relationships that gets expressed. So that can be interesting, and for the right applications, it works great. So Microsoft has that GraphRag project that has LanceDB as kind of the default option. We've had good integrations with KuzuDB, which is a new challenger to like your Neo4j kind of graph database, and that's columnar, it's in memory, it's written in C++. This new generation of graph database, and it's very fast and it's very good. But I think at the end of the day, that tends to be more of a niche application. Like typically the way, if people ask me, my answer is typically, if you're not sure you need a graph, you don't need a graph, right? Like it's very clear. It should be very clear that you definitely need a graph before you introduce that additional complexity in, because then you have to say like copy part of your data. You have to spend more time structuring that data into the right graph, thinking about the traversal patterns, and then training the team to support that. Now, one thing that's interesting is I do see growth in this area because LLMs and AI have made it much easier to create graph schemas and also write graph queries. So you don't have to really understand the graph the query language, and you can just a lot of times use natural language there. Okay, cool. So the last thing I want to mention in this iteration of the pipeline is, okay, so once you start down the road of like adding additional features, there's kind of no stopping, right? So here he ended up experimenting with a lot of things where, you extracted the text, but then you used an LM to say, hey, I'm going to create a summary. Then you use an LM again to say like, let's extract some tags that we can use. Right, and then you embed them. You embed the text, maybe the summary and the tags, into both vector embeddings through the embedding model, or make it searchable through a full text search index, and then maybe you'll open up filtering for these tags as well. And then now the application can ask questions, using a filtered hybrid search that greatly improves your. But then also not just about running it once, but making it work reliably as you add more data into that. So, if you think about all of this, like none of this stuff, um, outside of just generating the indices, a vector database has any good support to do. And this is actually where we see a lot of pain points from our users and customers that are like, oh, that we coded up the data pipeline wrong, and things went into a loop, and like over the weekend it generated like a $50,000 or $100,000 like OpenAI build because of repeated failures in embedding generation. And it also just makes overall iteration non-trivial, right? Because if you have a simple vector database that only supports maybe like one vector column per table, or it doesn't allow you to make a lot of changes and add columns, and it forces you to copy the data and re-ingest that data. That both gets expensive, that gets slow, and there's always a chance to introduce a lot of errors as you rewrite that data, right? And then imagine you're doing an experiment and you're getting like really surprising results, and you go back and you're like, I can't even reproduce the previous state anymore. Well, what exactly happened? Is it because your data changed, or like you messed up the code? Like you can track it through GitHub, that you can track the code changes through GitHub, and so you can always roll back to the Git SHA. But like if you had to blow away the table and reindex the whole thing, like it's very difficult for you to track the changes in the data to get that level of debuggability and reproducibility, right? And this is why a lot of our community loves the versioning features in Lance. Is once you have a set that you're happy with that you shipped in production, you can actually tag a version, and then as you add data, it's the new changes are automatically versioned. So if you get to a state where you find a bug, you can always say like, check out this version of the table, the last like golden set of the table, and then run some queries and see, okay, did I get the results I expected, and kind of do that sanity check and compare it between different states of your embedding store. Okay, and then the last thing is, of course, you can start fine-tuning this stuff. So that takes us to this next topic, which is, should I do fine-tuning? And that splits up into, well, should I use a re-ranker? Should I fine-tune the re-ranker? And should I fine-tune the embedding spaces? So of course, in Lance, we kind of support all three flavors where there's like a third-party API, right? So this is your Cohere re-ranker, Gina re-ranker, and then any model that you can pull off, Hugging Face, cross encoders, and I guess like technically on the third-party end, you can also prompt OpenAI or like ChatGPT into becoming a re-ranker model as well. And then number 3 is just your custom ones. So we have a blog post here with a bunch of benchmarks that we ran on the different re-rankers, and it's pretty interesting. So one of the interesting results is that like fine-tuning and custom training of a re-ranker works pretty well. So if you have a pulling off the shelf like model from Hugging Face, if you have real data points for re-ranking in the thousands, then you'll immediately start to see some lift. And of course, re-ranker models tend to be a lot lighter weight. And it's much easier to fine tune than both embedding models and of course LLMs. For the embedding spaces, like that gets a little more complicated, right? I think of fine tuning embedding space somewhat like trying to mess with CSS. Like you fine tune this problem that you see in this part of the latent space, and maybe you make some completely unintended changes in a different part of the space. And sometimes it's a little bit hard to see it unless you have really solid evals to cover most of your production use cases, right? But in general, if you have like, let's say like tens of thousands of real data points, you're going to see some lift by fine-tuning your embedding model. If you and especially I think if your data and if your question answers differ in distribution from like a off-the-shelf model, you're going to see some lift. So in finance, for example, legal, the languages tend to be different. And maybe in like science, right? Like if you're talking about chemistry and molecules all the time, that even the commonly used symbols are very different. The meaning is very different. So those are instances where we see folks having like good enough lift from fine-tuning the embedding model, then it justifies the complexity in which you undertake to do that. And of course, again, like once you go down this path, it's not the one and done. Once you start doing fine-tuning, you really have to kind of continuously evaluate it and refine it over time and do continuous fine-tuning and retraining. Cool. So kind of to sum it up, I'll try to speed up through the rest so we can leave a little bit of time for the demo. So what we feel AI data infrastructure is trying to meet is this what we call multimodal challenge, right? It's not just about text and vectors, right? You have images and PDFs and like slides and videos and all of that. AI unlocks a value in this data, but the data infrastructure we have today are not optimized with both storing and working with this kind of embeddings and blob data, right? I'm kind of grouping all of these under blob data, is that at the storage layer, that's what it looks like. So it's hard to do fast iteration. It's really hard to do it efficiently at scale. And then of course, it's slow to experiment with a lot of these things. And of course, it's not just about data types, and it's about workloads, right? So we have to think beyond just the vector search, how to get data, how to process the data before we can put them in to the database for search. How do we compute aggregates and metrics and like dashboards and explore those data sets? How do we generate features from the raw multimodal data? And then maybe how do we train models or at least fine-tune models, right? So vector databases are really only good at dealing with just like one slice of that. And so what you really need is, what we're building into LanceDB is what we think is the full breadth of challenges where you don't have to maintain multiple systems and you don't have to copy data between them. So this is why we're building LanceDB, what we call the AI native multimodal lakehouse, right? That's open source. Python, you guys are probably using already. There's Rust, TypeScript, and we have Java SDKs as well now. So the idea is you can store all of your AI data in one place on cloud storage, and it's a single source of truth for all the AI work that you need to do, right? All of that is powered by the open source layer, a data layer. So it's essentially a replacement for Parquet and Iceberg for AI data. So this is Lance columnar format. It's up to 1,000 times faster than Parquet for random access. The table format is kind of like an AI native version of Iceberg, where it's really good for schema evolution if you need to add additional feature columns to your data over time without having to overwrite and make copies, which are particularly expensive for AI data. And the last thing is just the indexing, which you're already familiar with if you're using LanceDB already. So that sort of 3-in-1 is what we call Lance format. Right. And around this, we're building the LanceDB, the lakehouse, to simplify data infrastructure for AI. Right. You're familiar with the embedded library. So the full product is, okay, you can put all of your data in the same place on S3. There's a LanceDB, a distributed LanceDB that you can use for hybrid search at large scale. There's a SQL engine that's optimized for multimodal data. You can use it to do key value fetches, even without search. If you have like a row ID where you need to do like application level or like feature store like fetches, that's also available. And of course, you can feed this into the PyTorch data loader. And then we don't have time to go into it, but there's also we're shipping an API on top of this to do large scale distributed data pre-processing, and so keep your eye out in the next month or so for announcements for this new API. Right, so we're replacing multiple things with just LanceDB. Really, like, you're putting this on S3, so there's no complicated system for you to manage, and it can kind of scale to zero. I think one of the questions too is on, like, what's the largest in-house or in-house self-hosted installation. So this is the self-hosted enterprise installation that we have is the numbers you see here, right? The largest data set we've seen for training is around 20 petabytes of videos and image data. The largest, like, vector table we've indexed is about 10 billion rows. I think our record for speed, our benchmark record for speed is roughly 3 billion rows indexed in about 3 hours with our GPU accelerated indexing. On the online side, the highest throughput we've seen on a single table, this is of course through a distributed system, is about 20K queries, search queries per second. And then max ingestion at 4 gigabytes. So this 4 gigabytes is roughly like the S3 limit. I think we can push it further than that with additional tricks, but this is just sort of like the fastest we've seen. Okay. All right. Maybe. So sorry, my slides took a little bit longer than I thought, but maybe, like, Ayush, if you want to, like, do the demos really quick, and then we can try to leave time for Q&A at the end. How's that?
Okay, sure, sounds good. I'll take over the screen. Thank you. Okay.
So while Ayush is getting that ready, so I think the first demo you're going to see is what we call semantic.art, and you've seen what you see a lot in, like, the Midjourneys and the image generation tool, where you put in a prompt and it gives you like the AI generated image. I think we built this, like, tongue-in-cheek kind of foil to that kind of, it gives you the same feel. You can put in a prompt, but instead of generating the image, it searches your prompt over a collection that we've curated of, like, master artworks, the human generated artworks from museum websites that we've crawled over the world. And so you're presented with images that most match your prompt with human generated images rather than AI generated image that best matches your prompt.
Yeah, so this pretty much ingests artworks and relics from various sources, from museums or art galleries and stuff. And it expects you to just write a poem or a prose or whatever describes the emotion that a particular artwork invokes in you. Or you can also use multimodal search, which is like you can just click a picture and then search from it. And it will try to find an artwork similar to that from real world artworks. So to test that, what I would like to do is I just prompted Gemini to just describe its favorite artworks, right? And I wanted to see if I could find these artworks in this app, right? So Gemini chose this persistence of memory, which is a famous artwork. And if I describe how Gemini described it, and I try to search for it, I hopefully will see something similar to that or that same artwork. And so it shows me a bunch of different variations. Because this is a very famous artwork, I see the original artwork here, which it found, and then I also see a bunch of variations from it. It's like this is another variation, and this is another variation. And we could do more of those examples, and then I'll quickly show the architecture of how this works. So this is another famous artwork called The Great Wave. And if I semantically describe it, I should see this as one of the results, which is I see a bunch of different variations of this again. And now you can also search using multimodal queries, which is I'll show you an out of domain example. So for example, this is something that Gemini described. This has not been ingested at all. And this is the artwork. So let me try to quickly run this query and see what it describes. So it gives me some portraits that are similar to that. Now, what I could do here is to combine both the semantic description of text. I could also combine that with an image. So I have this image here, the same artwork, and I can then control the search through both the modalities, right? And it will give me something similar to both of those combined modalities, so which is something like this. And these are all real artworks. So this works. So let me just quickly show you the architecture of this. So this is surprisingly complex for both retrieval and the ingestion part. This is just the retrieval part. So you basically receive a query or a query and an image, and then we just combine those modalities initially because we want to combine. We want to have a query that captures the mood or the emotion from both the modalities, right? So we first what we do is we simply combine those queries by query rewriting, and then we extract some specific keywords that describe the mood of the particular artwork, right? And once we got those two things, there are two pathways that it takes. We have a query router agent because we could run different types of queries on LanceDB depending on the complexity of the final query, the rewritten query. There are three pathways, just like you could run an FTS search. So if this basically follows, the query router follows the user intent. So let's say I wanted to search just about a particular artist, like Van Gogh or something, right? So this recognizes, the query agent recognizes that the user does not want to search for a specific artwork based on its emotion, but they want to search for a particular artist and their artwork. So similarly, if the intent is sort of not clear about whether it's sort of tilted towards textual or more heavier towards the image side, it will perform hybrid search, etc. Right? So we have this one pathway that gets the results which are overfetched, and then with the keywords we pre-filter those search results beforehand so that we only search on the subset that sort of pass for the mood, right? So or the emotion that the user wants. And finally, once we have got the overfetched results, we want to rearrange them in a way that, as you've seen in the couple of examples that I showed, that the best results appear on top, which is why we implement LanceDB re-ranker that sort of ranks all of the result set based on the mood keywords that are extracted from the final query, right? So this is, I'm not going to go into the exact definition of the score that we have, but this basically is a LanceDB re-ranker API. You can plug in any logic or any business logic that you want, and you can simply just attach that to any query object, and that's it, right? So we get the final result. So this is how this works. So this basically uses VLM through and through and gives you the artwork of your choice.
Thank you first so much, Ayush and Chang, for the presentation. That was super interesting, really helpful.